I have been a professor at University of Colorado for about 30 years and have been preaching a lot in the field of efficient biological manufacturing, consulting for companies, and developing some of the pioneering devices in the area. Now I've decided to practice what I preach and started this company about a year and a half ago. I am seeking about $2 million as an angel or Series A investment to accomplish these three goals. One, I have this device that is patent pending that is far superior, I know, from existing devices to achieve the same purpose. What I want to do is to develop a lot of data and convince everybody that this is better so they can adopt this technology. This technology is useful for achieving high productivity through high cell density cultures, perfusion cultures I will define later, in the manufacture of any number of therapeutic biological molecules like monoclonal antibodies, things like erythropoietin, insulin, GM-CSF, or viral vaccines. It's applicable to a large number of biological molecules. And the way we do it, the way it is better than the traditional manufacturing processes is that we use continuous process and a specific version, a better version of a continuous process that we call perfusion process. And that is our secret sauce. And actually our secret sauce is in achieving this perfusion through our patent pending new device. So the problem is the status quo. Almost all, 90% of the biological manufacturing, the likes of Genentech, Amgen, and others, they use the commonly known as fed batch cultures. These are batch cultures that are fed with media so that the cells don't run out of media. And after a certain time, they have to stop feeding because the reactor would get filled up. So they have to start collecting whatever product they produce. There's a lot of downtime, typically about 30% or more downtime in a typical batch campaign. And that time is for harvesting, cleaning, and sterilizing the stainless steel tanks, refilling the reactor with media, and then growing the cells from small concentration all the way up to high cell concentration, and then they turn on the production. So the production is only for 2 to 3 days. The rest of the wasteful time is additional 10 days. So it's a very inefficient system, the batch production system. And as chemical engineering professor, I know that continuous production is always better because we would have no downtime at all, and we would have a continuous high cell density. And even before I get into that, let me tell you that the concentrations of nutrients that we have in a batch reactor are always crashing down. The toxic products like ammonia, lactic acid, which all kill the cells, they are constantly going up, but that is what everybody uses. Well, 90% of the people, not everybody, 90%. In addition to the toxics building up, the dead cells build up. Cell debris, when the dead cells burst open, they release some of their proteins from the lysosome, and that contains enzymes which can chew your valuable products and reduce the quality of the product. So the solution is simple. Go to continuous cultures. And in addition to continuous, where you can typically, chemical engineers think of something coming in, things going out. Instead of everything going out, what we want to do is retain the cells, keep them inside the reactor, so that cells are our catalysts. They are the ones that produce the protein and secrete the protein. So that process alone, retention of cells, is what makes a typical continuous process into a perfusion bioreactor. And so these cell retention devices, that is the typical secret sauce that people use. And about the 10% of the companies that use that corresponds to approximately $25 billion per year in terms of the biologicals that are produced. They typically use membranes, hollow fiber membranes, through which cells and liquid will come one way, and cells will be rejected, and the liquid containing your product will go out. These membranes are not good at separating live and dead cells. They retain all cells. So with time, Well, they do some things great. That is, they remove the spent medium along with the product, fresh nutrient medium is added, but the problem is that membranes cannot remove the dead cells. They accumulate into the bioreactor, and after about 2 or 3 weeks, the hollow fiber membrane or a flat membrane, any kind of membrane you use, they would get clogged with cell debris, proteins, DNA, gunk, any number of things. And so you have to stop the whole operation, clean it up, throw the membrane away, replace a fresh new membrane. Once again, clean the stainless steel reactor, sterilize it, fill it up with media, and allow the cells to grow. And this is the process, which is practiced by the better 10% of the companies that produce biologicals right now. I have a better solution, and that is a selective cell retention device in which I can remove only the dead cells and even smaller cell debris. I can remove them continuously, and at the same time I can retain or recycle live and productive cells back to the bioreactor. And this is a technology called inclined settler. It's simply a plate, a stainless steel plate or Teflon plate, whatever you like. And as you send cells, live and dead cells up here, you can control the flow rate. The smaller dead cells don't settle down yet by the time the liquid comes to the top, and the dead cells can be taken out. The live cells, being bigger, therefore they settle a little bit faster, and so they settle down. And if the cells are not sticky, and many of the cells are not, in the first ones we tried were definitely not, they were blood cells, white blood cells, hybridoma cells. So they would roll down to the bioreactor. So we have a way of selective removal of dead cells. Our reactor is clean, even after months, 4, 5 months of operation. We really don't have anything there that can get clogged. We keep removing the dead cells and cell debris along with the product. And I published on this about 21 years ago. And about 3 years later, Chiron, which is now part of Novartis, has invited me over and said, hey, look at this. And my 1 liter reactor is now their 500 liter stainless steel reactor, and my inclined settler is sitting on top, and it works. He said, oh, the equation you published, that's exactly what we use to scale it up. People have always been asking me, oh, can you scale it up? Can you scale it up? Well, here's an equation. But here's a guy, a PhD in virology or molecular biology, who scaled it up, said it works exactly as you published. Well, this is not the end of the story. There is a small problem here, and the problem is that the way other people have scaled up and patented and used is what I call a really unimaginative. It's very rectilinear, and we think very wasteful in space. And so I came up with a better method. Here's a proof from Roche about an inclined settler. There's so much of wasted space. Instead, if you can have a highly compact inclined settlers all the way through, you can have the whole big settler replaced by a very simple device. And here is my obligatory San Francisco garage slide. And in this little device, I can replace the whole big thing that Roche, for example, published upon. So there are about 3 different competitors. One of them is really popular, ATF, or alternating tangential flow. That company has been acquired by Repligen for about $25 million last year. They had revenues of about $8 million per year. There are other lesser efficient competitors, and there are problems with each of them. For example, the ATF system has moving parts like a diaphragm, etc., that can break and needs regular replacement. Membranes used in all of them, they would get clogged, and the ultrasonic filters generate heat, and that's a problem. This is a very expanding field. Like I said, 10% of the people already use ATF or TFF. If we can convince them in their small scale to use our system, show that it is worth switching over, and replace their existing ATF with ours, that's one easy target. There are 90% of the people who currently use fed batch cultures. FDA has been pushing them, quality by design, use continuous bioprocessing, here is one way where you don't have product quality degrading. You have consistently high product quality because you remove the dead cells and degrading enzymes. And so there's a big push, and gradually some of these companies, with their sunk costs, will take away, will get into our field. In light of time, let me just skip and change some. I have thoughts about pricing, and we have a, right now the team is me, but I'm recruiting 2 others, provided I get some funding. I'm expecting funding from SBIR initially, and I'm here seeking funds from angel and venture investors. I'm seeking $2 million for 25% on the company with a board seat. And there will be easy early exits through acquisition, like we have seen for Refined Technologies by Repligen for $25 million, or we can organically grow into a CMO and any number of possibilities. Here is my financial projections, and I will stop now for questions.
Questions? John?
I do have a few. Maybe I could sneak in 2 quick ones. So when ATF was acquired for $25 million, what were their annual sales at that time?
So from the public announcement that the Repligen made, they said from July onwards, they were going to expect about $4 million. That's how I know it's the revenue from a private company. $8 million is the amount that they were expecting in annual sales.
Okay. And,
but that is only for the small 10% of the companies. I think the field is really ripe for big growth from there.
Right. I was just doing the math on your pre-money valuation today. I mean, because your revenues today are relatively small. Yeah.
I'm just now making the first prototype available for people who are interested in buying.
So the second question was on the intellectual property. So you filed a patent application on the engineering of this approach. I mean, how easy do you think it would be to come up with an alternate engineering design that circumvents the claims in your patent application?
So this is a device patent, and I have 3 different versions of this device patent. And for the last 20 years, people have been using what I would think of as the inefficient rectilinear design. It may be possible, but I don't see anyone doing it. In fact, I will continue to improve on this design, and will file more and more design patents. In addition, I will have process patents as well.
Great. Can I ask just a quick
please.
And are you yourself, do you maintain your academic position and doing this, or are you 100% in the company at this point?
I took early retirement last year, and I'm 100% with this company.
So you probably don't need a salary, right?
Well, I'm depending on my angel at this time, and I, of course, will take salary after some real money comes in.
Cool.
Other questions?
So for your prototypical device, is this an easy retrofit into existing bioreactors? Or do you need to, engineer a solution to, what could be a complicated series of vessels that are out there?
It's a simple modular device which can sit on top of any bioreactor, whoever makes the bioreactor. So it just adds a few pumps to send in liquid back and forth, and it's modular with any system.
Okay. And then a question, are you doing this completely by yourself, or do you have any advisors, any other team members?
I have a number of scientific advisors and a couple of business advisors, and I have some early employees lined up. As soon as I get some outside money, I'm planning on hiring them. 2 of them are in fact in the field. One of them is a scientist at Chiron who scaled up the original version, and he lives in the Bay Area, and he's interested in joining this company. He's a senior gentleman. And the second person whom I'll hire first, actually, is my first PhD student with whom I published this work 21 years ago. He has plenty of biotech experience and regulatory affairs experience, so it'd be a great shoulder for me to lean on to lead the team.
Sana?
Oh, sorry.
I have a question which might stem from naivete on this particular
Sure.
subject.
It's an inclined settler that is scaled up in a cylindrical fashion.
Yes, and I was wondering, is there a possibility that that mechanical design can actually damage the cells or whatever that you're processing through it?
Good question. There are no moving parts here at all. And the only thing that makes the liquid move is a pump. And the cells will not quite go up, only the cell-free or clarified liquid will go up. And this has been tested, proven in other systems, like in the flat rectilinear scale-up. So there are no moving parts here.
Okay, so just to summarize, so what you're providing is basically a cavity that fluid flows through, and the fluid contains the cell. So there's no way that they can lyse the cell mechanically or anything.
Exactly. There's a cavity with a highly designed space providing quiescent zero or close to zero Reynolds number so cells can settle.
I'm curious as to how you see the impact of disposables floating around out there now. There's quite a few people who are headed that way. The FDA actually wants some products to go to disposables. And also, sorry, apart from disposable reactors, there's a fair amount of people starting to use wave technology and how you see that. And I'm curious as to how you would see that breaking up. I mean, I happen to have lived in the world with the large stir tank, so anything that can be done to fix that joy would be great. But I am curious as to how you see yourself in the long run competing against some of these other technologies coming in.
So disposables, depending on my mood, I can say good things or bad things about it. They create a lot of waste.
Sure.
But if that's the way the industry is going to go, I can make this out of plastic. And I can sell many, many of them rather than my single use, rather than my stainless steel device. So I am fully geared up to getting into the disposable field.
Great. Because I'd be curious to know what you might think a unit cost would be on a disposable, because that kind of changes the economics quite a bit.
So the pricing I kind of jumped over. I have the pricing listed there for a 1,000-liter stainless steel, and the competitors sell it for about $200,000. They're hollow fiber membrane with a lot of controls, bells and whistles.
Right.
But most of the cost is their annual replaceables, like the disposable, single-use membranes, and at least $100,000 per year. And the life of the system probably is 10 plus years. And I am planning to sell it for something like, initially I could lease it for less than the cost of the annual consumable. And then once I demonstrate that it is really superior to the existing three technologies, then I will say instead of $200,000, you pay them for one shot plus $100,000 every year. I'm thinking I might sell it for about $500,000. But these are all things that I need to work with my development people.
Good. Question here? Richard?
On your schedule here, your EBITDA, that normally is revenue less costs.
Yeah.
But you've added in investment and.
So I would say net retained EBITDA. I was thinking about that exact question. Is that the right thing? So it's net difference between the cash on hand is probably the right way to say it.
I'm a CPA and.
So it makes a big difference. I have been an engineering professor, so I'm very picky on the terms, so I can understand your
I'm not sure if
sensitivity.
that was done in other slides from other companies
Yeah.
or not, but just a method.
So I was following the template that was given to me, and there I was very, very doubtful if EBITDA was the right term, and thanks for correcting me on that one.
Other questions back here?
Does this accelerate the rate at which larger particles separate from smaller particles?
I missed the first part of your
Does
question.
this accelerate the rate at which larger particles separate from smaller particles in solution?
Yeah, this works by differential sedimentation. So if my dead cells are about 8 microns or smaller and my live cells are about 12 microns, typical mammalian cell, diameter squared is what the velocity is, Stokes sedimentation velocity. So 12 squared 144, 8 squared 64, I have a big advantage in the differential sedimentation. And we have proven that at various operating flow rates, only dead cells come out on top, all the live cells go back down.
So, I mean, outside of biological applications, I imagine there's a tremendous market for industrial applications.
There are about 8 different applications in my patent filing that have said. One of them the one that I like most, and it's the simplest thing, is to clarify beer. You don't need a filter to get the cells out of beer. But for various, let's say, heterogeneous catalysis in chemical process industries, really big industry, you can remove the solid catalyst out from here, and wastewater treatment, and there are, yes, you're right, there are many applications.
So you separate 2 micron sized particles from 4 micron sized particles?
Yes, and it has been not possible from the previous design. With our design right now, we're working with yeast cells that are 5 micron, and the dead cells are probably 3 micron or smaller. And so it's very close, but not exactly. The smaller the cell size, larger the device you need. But because it's a 3-dimensionally scaled up system, all you need is add one more layer of rings and you're almost doubling the capacity.
So if you can fit this on one of our reactors, we'd be happy to try it for you.
I have one, we'll talk.
Very good. Other questions?
Actually,
No.
well, you mentioned that you want to use some of the proceeds from this round to generate data. I'm just wondering why you want to generate data rather than dollars. Well, why not? I mean, it seems pretty compelling.
So
Why not
the
go and sell it?
year 3 onward, before you will buy the instrument from me, you want to see my data.
Well,
At
I
least
wanna
that's
see-
what people have told me.
I want to see my data.
Yeah. So I will. So initial money you will be used to build more prototypes and get data from various cell types, and then we actually plan to sell these devices.
Great, thanks.
Okay. Other questions? All right, join me in thanking Dhinakar.